Welcome to Regents Review, Unit 8 on gases. So let's compare the states of matter. When we look at a solid, we can see that the particles are very close together. They're ordered, so there's not a lot of potential for movement, and that's because we have higher intermolecular forces of attraction holding these particles together, and so they essentially just vibrate in place. So solids have a definite shape, they have a definite volume, and if you recall, in terms of entropy, they have very low entropy. And we talked about entropy being this measurement of disorder, and since these are very ordered, they have low entropy. But really what entropy is how many possible ways can we rearrange these particles in different arrangements. And since the particles are very close together and there's not a lot of movement, we can't really arrange them in many different ways, and so we say that solids have a low entropy. As you move on to our liquid, you can see the particles are less ordered. They can kind of move or flow around each other. They have somewhat moderate forces of attraction. And liquids take the shape of the container, but they do have a definite volume. And again, that entropy, then we have, I would say, medium entropy. So we have more entropy than we do for the solids, but less than the gas. Because of this movement, we can then arrange these particles in more ways than we could a solid, and that's why the entropy increases. When we get to the gases, these are the furthest apart, the most disordered, and the most random and the greatest potential for movement due to a low intermolecular force of attraction. So gases will always not only take the shape, but they're going to fill the container. And in terms of that entropy, since they have all this movement, we can rearrange these particles in many different ways, and so the entropy is very high. And recall that gases are most affected by changes in things like temperature, pressure, and volume. We also talked about ideal versus real gases. Ideal gases are these imaginary gases, how we would like gases to behave. They follow the gas laws, like the combined gas law. The particles have no attraction to each other. They have essentially no volume. They move in straight lines, and they have elastic collisions where the energy is transferred from one substance to another. The real gases, how gases actually behave, are this huge spectrum. They can be close to ideal or very far from ideal. They do not follow the gas laws exactly. Particles do attract each other. We know we have some intermolecular forces of attraction, and there's ways we can limit that. They do have some volume. They don't always move in straight lines, and they have non-elastic collisions. So how do we get real gases to behave closer to being ideal? Well, if ideal gases are perfect gases and have no mass, no volume, and no attraction, how can we limit these things? And so the acronym we had was PLIGHT. So when real gases behave like ideal gases, we want them to be far apart from each other so we can limit the attractive forces, and we want them moving very quickly, again, to limit those attractive forces. And so what we can do is we can put them under conditions of low pressure and high temperature. So our PLIGHT is pressure low, high temperature for our ideal gases. And in doing so, we keep these particles away from each other, and we limit those attractive forces, and then the volume becomes negligible because the distance between these particles is much greater than the actual size of the particles themselves. And gases that behave most ideally are ones that have very, very little mass. So things like hydrogen, for example, would be a good example of an ideal gas under these conditions. What exactly is gas pressure? Gas pressure is just the force of the particles against the walls of a container. And we use units like kilopascals and atmospheres, as we can see here for our standard pressure on table A. And we have factors that affect our gas pressure. And these are everyday things that we see. For example, the number of moles of gas, like how much gas do we have? If we increase the amount of gas particles, the concentration, such as when we fill our tire with air, by increasing the number of particles, we're going to increase then the pressure of the gas. We have more particles colliding with the walls of the container, in this case the tire, and therefore the pressure goes up. Same thing for temperature. If we increase the temperature, we're going to increase the speed at which the particles are moving, that kinetic energy, and again, that's going to increase the force against the walls of the container and increase that pressure. So in the summer, our tires will inflate more because of higher pressure, and in the winter they look like they're maybe flat because the pressure decreases. In terms of volume, if we decrease the volume, like if we squeeze a balloon, the pressure then increases. Avogadro's law looks at equal volumes of different types of gases at the same conditions, the same temperature and pressure. And what he said is that if we have the same conditions, we'd have the same number of particles no matter what the particles are. So for example, I have 5-liter containers here at the same temperature and same pressure. But here I have neon gas and here I have xenon gas. It doesn't matter that the particles are different, we would still have the same number of particles because the conditions are the same. So typically for questions like this, they'll give you choices. Just look for the conditions that are all the same. It does not matter what the gas is. It could be CO2, it could be CO, NO2, it doesn't matter as long as the temperature, pressure, and volume are the same. In terms of the relationships between our two variables, either volume, temperature, or pressure, when temperature is involved in changing, it's a direct relationship. So when we increase temperature, we increase volume directly. And that's because when we increase temperature, the particles are going to move faster and generate more pressure. And that's going to change the volume. And this only works if we have a either movable container, like this with a piston, or a substance that is elastic, like a balloon. If the container is rigid, like a fixed container, then volume would not change, of course. Increasing temperature also increases the pressure because as we increase temperature, as I said, the particle is going to move faster and generate more force on the walls of the container. So again, when temperature is involved, it's a direct relationship. When temperature is not involved, it's an inverse relationship. So when one increases, the other one decreases. In this case, it's pressure versus volume. When we increase our pressure, the volume gets smaller. Or if we increase the volume, we have more space, and so the pressure goes lower. So it's an inverse relationship. One goes up, the other one goes down. Graham's law of diffusion talks about concentration of gases. So gases move from a higher concentration to a low concentration. So if these gas particles represent, let's say, some perfume that you spray, over time they're going to spread out and diffuse from the higher concentration here to a lower concentration. And the lighter gases will diffuse faster. And lastly, the combined gas law. The combined gas law is on table T, and it's P1V1 over T1 equals P2V2 over T2. The ones indicate the initial conditions, and then the twos are the final conditions. Recall we have table A to get our standard pressure and temperature if we need that. Temperature must be in Kelvin to avoid any negative values. And you have to make sure the units on the left equal the units on the right. So for example, if your question has pressure in atmospheres on the left, then we have to use atmospheres on the right. If it's kilopascals on the left, then we use kilopascals on the right. For volume, if it's milliliters on the left, we use milliliters on the right. Just make sure they are equal. If there is a variable that is said to be held constant, not changing, or is not mentioned at all in the problem, then we actually just cross it out of the equation. So for example, if temperature is held constant, we can cross it out, and then our new equation is just going to be the top part. So let's see an example. A gas in a rigid container has a pressure of 3.5 atmospheres at 200 Kelvin. Calculate the pressure at 273 Kelvin. So I suggest writing out the formula first, write out all the variables, and then plug in your values. Alright, so let's write out our formula, which is P1V1 over T1 equals P2V2 over T2. A gas in a rigid container has a pressure of 3.5 atmospheres. That's my initial pressure. So 3.5. Write your units so you know that they're going to be same on both sides. And it's at 200 Kelvin, as you can see here. So that's our initial temperature. 200 Kelvin. Calculate the pressure at 273 Kelvin. So notice volume is not being mentioned, so we can cross volume out of our equation. So it's simply just P1 over T1 equals P2 over T2. So we are changing our temperature to 273 Kelvin, and then we're going to solve for X. We can cross multiply. So 200 X is equal to 3.5 times 273, and that equals 955.5 divided by 200, and we get an answer of 4.8. And now we're looking at what are our units. So we're looking for the new pressure. Since we had atmospheres, it's 4.8 atmospheres. Okay, so we have a 32.9 liter sample of a gas at a constant pressure. So we're going to cross out pressure out of our equation. So it's just V1 over T1 equals V2 over T2. Again, I canceled out the pressure. And that's going to increase in temperature from 25 to 45 Celsius. So first, should the volume increase? Well, it's temperature versus volume. That's a direct relationship. So if we're increasing temperature, then volume should increase. Calculate the new volume. So we have 32.9 liters, initial volume. Initial temperature is 25 Celsius, but I have to add 273 because we want it in Kelvin, so that's 298. And then we're solving for V2, our new volume. And again, we're going to convert our 45 Celsius to Kelvin, which is 318. These are both Kelvin. Cross multiply. And we get an answer of 35, and our volume is going to be liters, so 35 liters. And let's see our last problem. A 45 milliliter sample of a gas at standard pressure is heated from 20 Celsius to 50 Celsius. The pressure of the gas increases to 107.9 kilopascals. What is the new volume of the gas? So again, our formula P1 V1 over T1 equals P2 V2 over T2. Initial volume is 45 milliliters. Standard pressure, so that means we're going to go to table A. And the standard pressure, since we're using kilopascals later in the question, let's use kilopascals. So that's 101.3. The pressure of the gas increases to 107.9, so 107.9. What is the new volume? X. And then our temperatures, we had 20 Celsius to 50 Celsius, so again, it has to be in Kelvin. So 20 plus 273 gives me 293 Kelvin. And then for the 50 Celsius plus 273 gives me 323 Kelvin, and then we're going to cross multiply. And we get an answer of 47, and we're looking for our volume. Since we had milliliters, it's going to be 47 milliliters.